It is now time to talk about the dependent motion analysis of two particles. So what does it actually mean? Well, a dependent motion occurs when one block or the motion of one block affects the motion of the other block. And this occurs, for instance, in a rope and pulley setup. So if one box, for instance, goes down, the other box goes up. And so this occurs only when the two blocks are connected by an inextensible cord. So the cord is assumed to be inextensible, so it cannot change in length. Now a couple of notes concerning the positions of the different blocks. The positions are measured here from a fixed datum or origin. So one selects the datum or the origin and measures the position of each of these blocks with respect to that datum line. The positions are also measured in the direction of motion of each block. So each block has a certain direction of motion and the position is measured relative to that direction. The positive direction is always set out of the datum. So if you take your datum to be up, the direction of motion would be outwards. And finally, one should keep in mind that the reference point or datum line does not have to be the same for all the particles. So one can define a datum line for each of the different particles in the problem. So we've seen a sort of overview about the dependent motion analysis. Let us now look at how one can extract the equations of motion in the case of a dependable analysis. So the very first step is to write down the equations that relate the position of the particles by simply summing up the different chunks of the rope. The second step, well, one needs to take the derivative of that expression to get the velocity equation. And then the third step involves the derivative of the velocity equation in order to get the acceleration equation. So dealing with dependable motion analysis is very straightforward. One should only remember the different bullet points that I have talked about a couple of seconds ago. So let us look now at an example to see how it actually works in practice. So as you can see in the image on the right, we have a rope and pulley setup, and we need to apply the different steps we've talked about. So we define a datum line for both particles and then set a positive direction, which is always further away from the datum line. Then the next step is to write down an equation that relates the position of the particles, and we do that by summing the different chunks of the rope. Remember, the only constraint we have in a rope and pulley setup is the fact that the cord length is constant. So one can write an expression of the cord length as a function of the position of the different particles. So in this case, by summing the different chunks, one can write that 2SB, which is the two first portions of the rope, plus H plus SA is equal to the total length of the rope, L. Now notice here we've discarded small chunks that are assumed to be constant. Then we need to take the derivative of that expression, which gives us 2VB plus 0 plus VA is equal to 0. And the reason why we end up with 0 terms for H and L is basically the fact that L and H are constants. Then we can take the derivative again and get an expression for the acceleration. 2AB plus 0 plus AA is equal to 0. And so finally, one has that VA is equal to minus 2VB and AA is equal to minus 2AB. The velocity or the acceleration of one of the particles dictates the velocity and acceleration of the second particle. And that's exactly what the dependability motion analysis is. So the sign here, it's very important to note that the sign here are related to the sign convention imposed by the selected datums. So if you've selected a specific datum, you know that the positive direction is out of that datum. And so whenever you get a negative sign, you know that it's in the opposite direction of that sign convention. And so you can end up with different sign conventions for each of the different particles, assuming you have selected different datums. Now you'll get a better understanding of what I'm talking about here after we've discussed another example.